Our next speaker is Emile Siboulet, a research engineer and PhD student at one of the most distinguished labs in robotics in Europe, LAS CNRS. So it's a honor to have somebody from LAS coming here all the way to Melbourne. This work presents an interesting take on a specific type of temporal planning problems where the task and associated trajectories of many unmanned aerial systems may be coordinated in order that the network connectivity is maintained at all times. This is a tricky problem relevant to the control of multi-agent systems, and I'm looking forward to learn more about the way Emile and his colleagues addressed it.
Thank you very much. Thank you for the presentation. So my name is Emile Siboulet. I'm going to present you a flow-based planning method for multi-agent progression with deployable agent and communication constraints. So our basic idea of this paper is to be able to produce plan for a specific mission, and the specific mission is a progression mission. The base of this was a coma mission where robots need to cross an area which is simulated to be hazardous and need to perform specific tasks. And tasks were performed with a red cube that we can see here. And the key idea of this is in a realistic environment, and you have to cross it. So we have to take into account complex tasks at certain position, and also the fact that we want to have a specific trajectory plan for every agent. What we observed on the coma mission is what we have to take into account the nature of our agent. We have to make 3 different Coupvent agents. We have the leader, which is basically the one responsible for commanding, and because it's in an hazardous area, you want to protect him, or you want to be the less likely to discover new position. You have carrier agents, which are basically big and heavy agents, which are on the ground and are able to perform tasks where the commanding agent is not performing tasks to be able to interact with the other and take position. And you also have deployable agent, which is way faster, but if you don't take into account that you have to deploy them and recover them, and also that they have limited amount of autonomy, you are going to face enormous problem in the plan that you're going to produce. So our DSL, our domain-specific language, is based on the work of Christophe Godet, and our contribution that I'm going to show you is how we are able to modelize deployable agents and how we are able to modelize communication constraints, so to have better quality plan and better way to solve the problem. So first, I'm going to show you our problem formalization, how we are going to specify the domain. Then I'm going to show you how we implement constraint model, so to be able to solve it, and then we are going to discuss the experimental result and how fast can we produce this plan. So first of all, because it's a progression mission, we have to define a specific graph for the different agents. We have to define the start of the start position here. We have to define the end position here. And we also are able to define partially traversal edge. A thing that we encounter is a lot of deployable agents are going to pass on forest or on hard traversability terrain, and we have to take this into account so to be able to be faster. Then when we finish to define our graph with a lot of interest points where we want to be, to go, we are going to define specific tasks to do. So basically take some picture, and we also have some restricted area where we are not supposed to be from time to time. A key point of this mission is we have tasks are only defined on vertices, so we know where we are going to perform them, and all tasks have a specific temporal window, and we have to manage to do it in this temporal window. And if we have some more complex tasks to modelize, we are able to synchronize them, or we are about to say that we want this task to be previously done than this task. What we want to be able to do with deployable agents is basically this. This is an example of a plan. So basically you have the carrier agent that is going through the entire zone, but we want to be able to deploy a drone and to take it back. So the rule is we have flight time for our agents, and we want to be sure to retrieve it before it reaches its maximum capacity. And we have a number of deployments for each agent, and we have a dedicated carrier for each agent, and they cannot swap deployable agent. And for our modelization of communication, we choose to define another graph, which is the intervisibility communication graph. And the rule is if you are in direct communication with the leader, you are OK. And if you are not in direct visibility to the leader, you are not. We are not using mesh network or way to communicate in groups. We are only able to communicate from the leader to agents. And we want communication at any time in the mission. So the plan that we want to produce is the arrival time of every agent at each edge, the duration stayed by every agent at each edge, the time of execution of task, and which agent is realizing which task. And of course, we want a valid plan with every action executed inside of it, and the optimal plan is the quickest. So now that we've seen how we define our mission, I'm going to show you how we encode it in a CSP. So a key factor of our approach is we want to be as fast as possible, and so we made a DSL, and I'm going to show you the second block of our approach, which is the CP encoding. And a key factor of our approach is we are deducing the plan from the value of the CSP returned by the solver. So the base of the graph, and because we are using a graph, we are going to use binary flow encoding, which means that for every agent and every position, we are going to enforce that a flow is going from the start position to the end position. And if we are able to produce all the variables to respect the constraint of every flow inside is equal to every flow outside with a binary flow encoding, we know that we reach a continuous path from the start to the end. To get the temporal part of our plan, we are going to propagate the time. So basically, if the solver found a solution with, if the solver found a solution where the edge is used, we are going to calculate the time of arrival at the next position by adding the time arrival at the previous position plus the duration stayed on plus the arrival time. So, and this is how we compute the first part of the variable of our problem. The realization, the model that we did for the task realization is just a durative action. The agent have to stay enough on the position to be able to perform it. And we are monitoring if the agent stays enough and if it's in a real-time window. A key assumption that we made for our problem is we have a synchronization on the start, on the arrival on the position. So we consider that the task will be executed on the arrival on the position. And this is able for the next time. So now I'm going to describe you how we made our first contribution, which is the modelization of deployable agents. So I'm going to use an example. This is a simple plan where the carrier agent is going from V1 to V4 and is performing a task at V3. And we can see on the bottom the timeline of what we are going to do with the carrier. And a common situation that we encounter was we have another vertices where the carrier agent could not go, and we wanted to be able to perform a specific other task with an agent. So, as I described for you, the idea was to have a deployable agent that, for instance, will be deployed on V2 and be recovered at V3. And if we got this, we got our operational task done. But the issue is with this graph at this state, it does not respect the two first constraints that I've presented to you. So we had to introduce factice vertices. So basically, we have a factice start position with it that is enforced for the carrier agent. So the carrier agent is going from V start to V1. But for the deployable agent, we introduce deployable task that is able to link the deployable agent from the start position to its deploy position. And so this is how we deploy agent, and this is how we use previously depicted equation. And we do the same for the recovery time of the agent. So for the recovery, we also introduce VD, which are storage position for the deployable agent. And in this example, the agent is stored here. And this is with this that we are able also to have multiple deployments. For these instances, the solution shows that we are going from the storage position to the end position. But if we need to have another deployment, we are going to have another edge that is going from VD to the other position. And the key idea here is that with now this representation and what we introduce, we are able to respect the two previously presented constraints, and so we are able to use fast CSP solver on this kind of domain. The other key approaches is communication. So for instances, it's quite easy to get communication constraints when you have two positions. Here, for the example, you have a leader agent on V1 and the carrier agent on V3. And the idea is that we allow the carrier agent to stay on V3 for the duration that the leader agent is staying on V1. So this is basically our definition. And for instances, if the leader moves to another position, we can enforce also these constraints on the other position. And the issue with this is, you can see that we have a time window where the agent is not allowed to stay on the 3 because it's not directly linked to a position of our carrier, sorry, of our leader. So the idea is that when we have a leader movement, we are allowing the agent to stay only and if only there is a communication between the first starting point of the leader and the going point of the leader. And this make us able to represent it for the whole time, even if our agents are not on position, which is not the usual way to do it with CSP. And the key thing that I want you to remember on this slide is that the communication constraint is not from one point to the other, but is with 3 positions. And so we are, for the mission, we are only enforcing communication constraint on 3 positions. So basically, if you are able to, yes, thank you. If you are able to produce, if you are able to encode your problem and have all this, we are going to produce plans. So our approach is called Zortag, and Zortag is basically an encoder which takes the problem, convert it to Minizinc, and then use the CPSAT from our tools to solve the problem. We wanted to compare ourselves with another more classical planning approaches, and the solver that we selected was Graviers, which is another solver from the LAS, and we choose this solver because we are going to have to modelize hierarchical, numerical, and temporal planning, which is like a few solvers that are using PDDL are able to do this, and to be able to have really appropriate modelization, we use UP planning because it makes us able to be as close as possible from what Graviers is able to do. So for the domain, I don't have enough time to present it to you, but what I want to emphasize is that it's a domain independent approaches, so it's expected to have to be less efficient on this kind of problem. And Graviers says it is using a CSP approach and also a conversion from the planning domain to CSP problem. A key feature of domains, and we wanted to stay as close as possible from our approach, so from Zortag approaches, is we cannot revisit a position. The movement is not is not performed recursively, as usually is performed for classical planning and HTN planning. And so with this modelization, we also can prove optimality with Graviers because we are reducing the search space for the movements. This is the graph. I don't have time to comment it, but this is the graph that we are the target graph of our experimentation. We can talk about this later. And the key idea is we wanted to have basically a window of solvability time. Basically, we are on the mission. We want to help user to perform the mission, so we want to be as quick as possible. And the thing that I want to point out is we are faster than Graviers. So our approaches is in the blue, and we have in light blue a coverage. So we are able to find a lot of solution. And in dark blue, we have mean quality of solution, and we can see that both approaches are able to produce plan and to improve plan quality really fast. A thing that I want to point out is there's a difference between Zortag optimality and Graviers optimality. Graviers is producing the optimal plan for the mission, but with our approach hypothesis in the CSP model, we are downgrading a little bit of the plan quality that we are producing. I want to emphasize that it's a marginal gap, and we have a way quicker finding solution. And key feature that I want to point out, and we have did some experimentation on different metrics, first plan, last plan, and proven optimal. And we also did the equivalent quality plan found by Graviers. Because Graviers is able to produce better quality, we evaluate when Graviers did find the exact qualities that we are able to produce with our CSP approach, and it was way longer. So in order to have a good quality plan with Graviers, we have to stay long, so it was not really an approach that can be, that was possible. And so we also generated a random benchmark because the previous experiment was on a specific domain and problem, and we also generate a lot of other problems. So what we have found is that Graviers is consistently worse than Zortag, and the coverage of Zortag is way efficienter. But I want to also say that because we use Minisync, we were able to connect other CSP model on our approaches, and we are significantly worse than RES. So it has to be discussed because the Zortak approach, so our CSP approach, was made for OR tools, and it might be that the encoding in CSP was not designed for short-code G-code, and another encoding might have been better for these approaches. So in conclusion, we have defined the Zortak approach with a domain-specific language that leaves solution in a acceptable time frame for our mission, and we want to try it on it. But I want to emphasize that RES and classical domain are also able to provide better quality solution in a reasonable amount of time. We have future works, and thanks a lot for your attention.
Thank you very much, Emile, for the talk. So, any questions from the audience?
First, thanks for the talk. I would express my sympathy for the loss of Simon Lacroix that was unfortunately... okay. Sorry about that.
Yeah, thank you very much.
Anyway, I would ask basically the same question as the first talk. There are other approaches providing ways for formalizing temporal problems, also providing properties for controllability. For instance, the dynamic controllability that you may have in order to deal also with temporal uncertainty. So when you don't know exactly the duration of a task, so the question is basically what is the added value of using a different formalization apart using, for instance, a CP approach, but actually temporal networks are usually used with CP approach. So my question is, what is the critical point in using a different formalization? Thanks.
Thank you for the question. We basically wanted to see how well perform an old approaches, because using binary flow encoding is quite old approaches, and CSP solver have evolved quite a lot, especially OR tools. I had like a major improvement in my solving time by update of OR tools. And so we thought that this approaches was fast enough for our domain. The issue with, we used RESs. The first approximation that we did was to use the classical planning approach with RESs, and we did not have sufficient performance to use it on the ground. And so this is why, and I'll be eager to test other approaches, and maybe even like planning will not be optimal or efficient for this kind of problem, but because we reached a point where it was able to work, now the next step will be to make it work in real life, to see if our modelization is enough or if we want to rework on it.
Thank you. If you go back to the slides with
This one?
yes, it seems to me here that you're a little bit sacrificing optimality for solving time, right?
Exactly.
Have you tried sacrificing all optimality and try, I don't know if there is a way, say, okay, don't care about the optimal, let's give me the first solution and understand how fast it is and what is the quality if you try just to do that?
It's thanks for the question. It's not that trivial. The issue is that, for instance, if I take my approaches, because I maybe more familiar with the Zortak approaches, because it's have multiple way of searching, and especially the back way of searching, so back propagation of time. So basically, start to do the path from the end and then reach it. The usual plan is a lot of tasks in the beginning of the mission and a lot of tasks at the end. And the second best plan is way better because it's just matching it to just smashing it, so to be extremely efficient. So we have a big increase in quality at the beginning, and we have big increase of quality at the beginning, and then it's slow, but it's not. We don't have any like certainties. If I have the time to just describe it like 2 to 3 minutes, this mission is particularly hard because you have the agents that start here, and that want to reach this position, but in this position, so the central position, we have a temporal restriction in the middle of the mission. So basically, you are not allowed to be in the center of the map during the mission for a period of time. So you have a lot of working plan that is just delaying for the for a few times for the mission, and then when it starts to produce plan with better quality, you have a big gap in the quality of plan at a specific moment where it finds new solution. So we try to evaluate how much we were able to improve plan, but the generality is sometimes it's really, really efficient and sometimes it's not. And I don't have any clear answer for you.
Okay, thank you to the speaker. Any other questions from the audience? Yeah, quick one, Andrea.
Yeah, a super quick follow-up that was triggered by Matteo's question. So is this delta gap in quality tunable in your encoding? So can I sort of augment it, accept that I will be more suboptimal in favor of speed, or it is something that is somehow inherent to the encoding itself?
Thanks for the question. It's inherent of the models that we did. Because we choose to have synchronization task at the beginning, we have this quality, and we have a big discrepancy next, because even if like you wait like for 10 or 20 seconds, maybe which on a 20-minute plan, maybe you are going to miss a temporal window where you are going to have to wait for an action to be completed or something else. So because you have a small amount of modification, you are going to have big one because of planning how it works. So if you want, for instance, to have better quality plan, you can introduce more variables. For instance, delaying variables and to be specified by the planner. So you have to wait, and then you are starting your task 20 seconds after being on the position. So there's workaround, basically.
Thank you very much, Emile.
Thank you.
Well, thank you everyone.